Welcome everybody. Waiting for a few more people. So this is a new product launch. This is our air to water heat pump water heater. Um, so this is our level 2. This is what we call our waves presentation. We're going to cover water, air, the vapor compression cycle, which is the refrigerant cycle, then electrical, and then service clearances. So I hope you'll find that this is intentional, purpose-driven, and again, open forum. I welcome the dialogue as we launch this new product because there could be code body issues that might drive certain aspects in your territory. I'm really not trying to bog you down in minutia, but rather I really want to give you the essentials you need in your region for a flawless install. Okay, and I think with that, we'll get started. So Rheem has really done a very good job moving forward with sustainability. Many of you have heard me talk about sustainability, and it's not just, buzzwords. These really have some weight to them. And I guess what I would say is this. Many of you know me, you've driven with me, and I have a bit of a lead foot, and I'm pleased to tell you that in the last 5-10 years, I really haven't had a speeding ticket, so my record is pretty clean. In that same capacity, I would suggest that Rheem and Raypak are concerned about their record. And moving forward, we're going to be able to look 5 years from now, 10 years from now, and look at our record for sustainability. What have we done by these high efficiency products and correct installs? The specifics on heat pump sustainability is pretty interesting. If you look at the decarbonization and electrification going on, this is a really big deal to get us off of a fossil fuel platform and move us into these other technologies to offset all this, these decarb goals and everything. So hopefully you'll find value, that we're not just talking bullet points. We have some real weight behind this as we move forward as it pertains to sustainability. I always like to start out with what is it? What is it we're talking about, and how does it work? And a heat pump water heater is really just a device that transfers heat from a space into a storage tank. So we're taking the ambient air temperature, we're extracting heat from it, we are rejecting that heat from a heat exchanger, and we're going to place that heat in a storage tank in the form of domestic water, hot, usable domestic water. At this time, this product is for space heating only. Down the road, it very well may be that we have a different animal to work with for space heating, for hydronics, and those types of things. But at present, in this launch, it is for domestic water only. So we know that for circulation, it's also called the circulating tank concept, we have a very low mass heater, very low water content, and we need to harness those BTUs, or rather harvest those BTUs, and place them into that storage tank. So that's what we're going to talk about. We're going to have a circulator. We're going to take that heat we're securing out of the ambient air, and we're going to place it into that storage tank for domestic use. How does it work? Well, we're going to register a call for heat. Typically, a sensor in the tank is going to tie into this unit, much like you would with a natural gas or propane heater, or even electric. If it has a set point and it falls below set point minus the differential, we're going to actuate a call for heat, if you will. In this instance, domestic water. So if this tank has a set point of 140 degrees with a 10-degree differential, as hot water leaves the tank and cold water fills the tank, we're going to draw down in temperature. We're going to get to that 130-degree temperature. We're going to actuate a call for heat to a unit or units, plural. We're going to engage the circulator. We're going to start pulling flow from the tank and our cold water supply, as the case may be. And we're going to start harvesting the BTUs out of that ambient air and we're going to place them into that tank. So if I were to boil this down very, very simply, if you're not familiar with heat pump technology, let's just say that this is an electric heater that has an ambient air assist. We're going to use that heat available in the ambient air, and we're going to harvest those BTUs and send them into storage. So it's really not any more exotic than that, but we're going to break it down very quickly. There are a couple different models in terms of how it works. We have a horizontal unit and a vertical unit. Here you see a unit that we're taking in that air from the side and exhausting vertically discharged out of the top. The other unit would be the opposite, where we're going to discharge on the horizontal out of the side. And sometimes the heat pump technology might seem a bit intimidating, but the beauty of this system and its design is that the refrigerant side is all self-contained. An installing contractor is not going to need to interact with the refrigerant. It is a self-contained closed circuit where the compressor is going to take that vapor compression cycle, extract that heat, and send it into one side of a brazed plate exchanger. On the other side of that brazed plate exchanger, we're going to be pumping our fluid in, counterflowing, extracting the heat, and then sending it out to storage. So that vapor compression cycle is not something you need to be concerned about. Down the road, we'll talk about startup, commissioning, service, and maintenance. And we have a way to check those pressures of that refrigerant. But as it pertains to installation, it's not something someone needs to be licensed in the refrigerant to install this unit, as it is all self-contained and sealed. Okay, I'm monitoring the question board here. So again, if you have any questions, go ahead and post them or unmute yourself and go ahead and ask. We've got plenty of time to do open forum Q&A. I don't want to rush through this. I want everyone to have a high level of comfort with how this is to be installed. Okay, and then as we said again, the fan discharges the cool air after we extract that heat from it. So in principle, it's very, very simple in terms of refrigerant flow path, the water flow path, and the air flow path. All of those things in harmony will result in, you know, a stored water temperature that will give us usable domestic water. Again, just another example here. It will end when this tank satisfies and we reach that set point. And then we'll go into essentially a post-purge with the pump, very similar to what we already know. So again, nothing exotic there. So here are the models for the unit, the dimensional data. We can start out with footprint, but I'll come back to service clearances at the end. But you can see that these are very modestly sized, I would guess you would say. These can be placed indoor. They're rated for outdoor use as well. Since the higher the ambient air temperature, the higher the efficiency and the more heat we'll be able to extract from it. And we'll get into that a little bit more deeply as it pertains to the air temperatures in this presentation. So WAVES, this is going to be a new acronym that you're going to see from Raypak and the Rheem side. And this acronym is very similar to our WAGES presentation. If we're dealing with a natural gas or propane combustion system, we have water, air, gas, electrical, and service. Well, here, since we're not using a fossil fuel, we can substitute the G and we can put in the V for that vapor compression cycle, which again is our refrigerant. So we're going to walk through each of these. We're going to break them down into very manageable bits, something that we can then digest and move forward with together. So again, open forum Q&A, unmute yourself if we have questions, but I do like to cover the basics. So these units in basic terms will give you capacities of so many thousand BTUs per hour. But as you'll see by the end of this presentation, a lot of that is going to be driven by what our supply water temperature is, what our ambient air temperature is, and so on. So in basic terms, you might see that we have a 60,000 BTU unit, 130,000 BTU unit, but again, your production values, your efficiencies, and net usable BTUs are going to fluctuate, and that's going to drive even higher efficiencies, which we'll talk about as well. On the water side, we are looking at some fairly high flow rates. You might notice that for a 60,000 BTU unit, we have some very proportionally high flow rates compared to our fossil fuel counterparts. The reason we do that is that we want these higher flow rates to run a very narrow temperature rise across that appliance. Again, that's going back to the basics in the math. The higher the flow rate, if our BTUs out are constant, if we decrease the flow rate, more temperature or more BTUs can get on that bus. If I increase the flow rate, I'm going to have a narrower temperature rise because not as many passengers can get on that bus. So we are talking about a multi-path system between the tank and the unit itself. So a multi-path design is something we're going to talk about. So we like to talk about flow. Now the unit that we are selling will have the optional circulators that we'll show here. And these are made for us by Grundfos, and they have some very good capacities. Yeah, I see a question. Go ahead.
And you can hear his audio.
Yeah, I'm trying, but I'm not getting it. It's
Paul?
Yeah, I can hear you. Go ahead, Kurt.
This is Kurt. So evidently this meeting, this presentation was also sent out on Teams, and there was about a dozen people who were on Teams. So I see Tim Cox and Noon Musa and a few others, David Kelly. They were initially watching this on Teams and could not get it. And so I'm trying to find people. There's a few people left on there and send them the Zoom invite. And but the people who have connected just in the last couple of minutes don't have sound.
Okay.
So I can
The
hear
webinar link should be on that Teams invite in the body of the invite.
well, I don't want to say.
That's correct, David. And then
Okay,
Kurt,
so
you have to make a selection. You have to make a selection for the audio for this software. Otherwise,
right,
it's
so I'm going to give everyone a minute. The other way to access this, if you didn't receive the invite, is to go to our raypactraining.com site, and you can go to our calendar and click on the invite there and dial in. So if someone needs to drop off and re-sign in and then re-access the audio, we can sure wait a few minutes to accomplish that. That's not a problem. Kurt, thank you for bringing that to my attention. Right. I appreciate that.
Thanks.
Yep.
And also, if you're on Teams and you go to GoWebinar, I had both of them open and it was echoing, so you'll have to drop Teams once you get into the webinar.
Excellent. Thank you, David.
Well, thank you.
Yep. Okay. Well, I'll kind of pause here while people maybe regroup and go to a different format if they have audio. Maybe ping me in the questions section if you still don't have audio. This presentation is being recorded, so it will be available on our training site as a recorded webinar that you can access. And I'm certain we're going to be doing this more than once. So I do apologize if you're having audio issues, but it is something that we can rework and revisit. And moving forward, I'm getting a very good friend of mine, well, kind of a friend of mine, David Baker, saying, is that a relative on the wall behind me? Thank you, David. Sometimes he's pretty funny, and of course, then there's now. So David Baker is an old friend of mine, and when I say old, I mean old. He's old. So thank you for your commentary, David. I'm sure we'll talk later. But that's actually a picture my son drew for me with charcoal. So That means a great deal to me. Circulators, again, back on task here a little bit. We are offering the Grundfos circulator, but we do have options. Again, based on flow and delta T's, we do have some other pump options that have been vetted by our engineering team, and I do have them listed here. Now, be aware, and this is kind of going to get into the application side here also, is that we have a unit. The heat pump itself potentially can be located outside, and that will elevate those available ambient air temperatures, but then maybe our storage tank is a certain distance away, right? So that might be a very plausible factor in our different applications. It might be on a different floor, different elevation. So circulator selection is going to be very important. And this particular bandwidth of selections is 100 equivalent feet. So we can talk about pressure drop, but more or less, if we look at 100 equivalent feet, these would be the circulators from your, let's just say your primary brands, Taco, B&G, Armstrong. Now, again, I am not limiting the other manufacturers that might be out there. You might have Velo, you might have Gould pumps. You know, there's a different pump availability out there. So this is a good baseline to do a cross reference to. And again, I do list the flow and head requirements on slide number 16. Okay, so here we are looking at 100 equivalent feet. And then we also have some flow and head requirements if you're 150 equivalent feet away. So again, I'm going to now go to the 150 equivalent feet away. And there's a modest change in some of those circulators. I'm highlighting the difference here. Instead of 100 equivalent feet, we now have some changes in the circulators for 150 equivalent feet. And that would be, you know, instead of a Tago 0011, now you're looking at a 0013. And as this is a domestic system, these would be bronze circulators. Then we went to an NBF 45, but now instead of speed 2, now we're on speed 3. And then finally, the Armstrong, previously it was an E7, and now we're at an E8. Okay, so again, modest differences in our pump selection to get us that narrow temperature rise of between 5 and 8 degrees that we're looking for in these systems. Again, this is a multi-path design. So when that unit calls for heat and we're getting that water out of the tank, it's going to take multiple passes to get that stored water temperature back to that usable set point. Excuse me. Does that make sense? Very good. Yeah, many of you know me. I think water chemistry is a topic that is mission critical, absolutely important. And in our manual, in the use and care manual, they have these values published so that if you have over 15 grains per gallon of hardness, it needs to be conditioned. Do not exceed, or do not go below a pH of 6. That's actually a bit of a misnomer there. 6 is on the acidity scale. It's not parts per million. I need to amend that. And then chlorides, we want to be less than 250 parts per million. So here is our straightforward water quality parameters. Please be within these parameters. This is what the unit is designed to handle. We all know the result if we don't, right? We're going to have a higher probability of scaling or minerals precipitating out of solution. As it pertains to water, you know, we did see that cover off on this type of slide where we saw that brazed plate exchanger. Well, now with the skins back on, if you will, here's my inlet down low. I'm counterflowing up through that brazed plate exchanger. And now here's my elevated temp fluid going into that storage tank. So again, very easy to follow for my inlets and my outlets. I'm going to go ahead and take another moment of pause here. Kurt, David Kelly, I I haven't seen anyone respond or any chat that is saying no one has audio. Is everyone good on audio now? Okay, I think we'll take that as a good sign and thumbs up.
Yeah.
So we'll keep moving forward.
Awesome.
And then again, we've been talking about those flow rates, a little bit higher flow rates than we might be accustomed to, but we want to see that temperature rise in this multi-pass system between the unit and the storage tank of a 5 to 8 degrees Fahrenheit rise. Again, that's why we're having these flow rates that are a little bit higher than what you would normally be accustomed to. And here's an example of a piping diagram. And we are working on getting some higher quality images. But again, it gets a little bit busy with these multiple pumps or multiple heat pumps and multiple tanks. But again, very easy because we're used to this. We're used to that reverse return principle. So we're bringing our cold water supply in. We're feeding that tank. Hot water going out of the tank as it's heated. But once this draws down in temperature, here's my sensor going into my lead unit. We'll talk about wiring and sensors here in a little bit. So when I actuate a unit, as the demand is needed, we'll engage the circulator. We'll draw water out of that tank, pass through the unit, take our hot supply, and then right back into storage. Again, so we're circulating tank concept in and out of that storage tank to these units, 5 to 8 degrees at a time until we elevate that temperature and satisfy on demand. It gets a little bit busy, but we can break this down more simply. Does that make sense to everybody? We should be familiar with these type of piping drawings. And we do have one where we are looking at a low ambient air boost system, where we would have a booster heater, typically it would be electric. You will see that this is circulating between the heat pump and our primary storage tanks, just like we described earlier. But now, if we get to a low ambient air temperature and we are not harvesting the necessary BTUs relative to the demand, now we have a booster heater that we can draw from that is not going right out into the system. It's actually piped in reverse series to go back into our primary storage tank. So we can use this as a booster, store those BTUs, and when the ambient air temperature is such that we can no longer keep up with the demand, we'll engage this circulator and we will essentially reload our primary storage. It looks a little bit busy, but as a narrative, it's really not that far out of the bandwidth of what we normally do. Does that make sense to everybody? Okay.
Yes.
I do. Okay, go ahead. David Kelly, any other comments?
Oh, no, that makes sense. Thank you so much.
You bet.
Question, so as soon as it goes in low ambient temp, the 2 pumps on the main heat pump shut down?
That's a fair question. We're going to talk about air next, but the refrigerant that is used in these heat pumps is R134. And it basically has a temperature, ambient air temperature minimum of 40 degrees. Otherwise, we potentially can need to do a defrost cycle. So anytime we're below 40 degrees ambient, you're really not going to get the production out of these units. And again, we're going to talk about this more thoroughly in the next segment on the air side rather than the water side. But at that point in time, we can do gas-fired backup. We can do this ambient boost temperature, typically an electric heater. So we'll talk more about other applications moving forward as well. But it will become more clear to you why we might need a booster heater when ambient air temperatures, let me state that again slowly and a little more clearly. When ambient air temperatures drop below a certain threshold, where we're going to need some redundancy and some backup.
Right.
Okay.
No, I understand that. I was just asking though, but in the sequence of operation, as soon as your low ambient tank kicks in or your gas, whatever you're using for a boost, do the two pumps on the heat pump stop running so it's not continually drawn out of the tank while you're trying to reheat the tank?
That would be correct. I'll
Okay.
go back and look at that here because now I have this
Right.
circulator reloading these tanks, right? So hot coming out, here's my return, reloading the tank with the hottest water until it presumably gets back up to set point in our stored usable hot water.
I have another question.
Sure, go ahead.
So if you are turning it off to the heat pumps and you're in an area, well, you could have it so you have most of the area hot, but you're in actually a freeze zone. Don't you want to keep some running to keep them actually the heat pumps from freezing with inside? At least run them at a lower level.
Right, and that's an excellent statement, Brian, and I like your choice of words because then we're going to talk about a defrost cycle. And yes, I want to make a distinction where the unit might hit this defrost cycle, and yes, it would take the circulator's operation, but at that point, it's more about the function of defrost rather than BTU production trying to reload a storage tank. Does that make sense?
Yes.
Okay. I know we have some really seasoned veterans out there, Jose Barbosa, Eric Connor, if he's out there. They might be able to speak to this more clearly. I definitely would invite their commentary if they've experienced the, the defrost cycle. Let's see if Eric Kelly is with us. No, I don't see Eric with us. But again, in principle, once we get below a certain ambient temperature, and a defrost cycle, we're going to use an external source to reload those tanks, or we could then go to any other form of backup. One form of backup that has been discussed is a electric point of use. Now, this is a little bit different, and I'll let you dissect this because there's a lot going on here. Now, everything that we've talked about previously is with that 5 to 8 degree delta T from the unit into the tank, right? So that's multiple passes. But in this application, when we no longer have those multiple passes active, and we need to get in a single pass that stored water temperature will state and then out, this is a configuration that's being introduced as a single pass. So when these heat pump water heaters can no longer keep up due to ambient air, then our electric point of use can be engaged. And then we now have in one pass reloading of that tank and then on out to that system. So more to follow on this when we talk about the electrical side, because I want to be very thorough in terms of the what, why, and how. This seems like it's very busy here, but if we break it down into modules, I think you'll find it to be very manageable. Header size, again, not necessarily in the manuals, but in our piping diagrams, in keeping with how Raypak does things, you can go to raypak.com, go to our piping diagrams, and in the upper left-hand quadrant of those diagrams, you will see those header sizes. So if I wanted 2 units that were the 135,000 BTU horizontal, I would need a 3-inch header, okay? Now, be aware that these smaller units, these 60,000 BTU units, they come standard with 1.25 tappings. That is our tapping size at the unit. But we are recommending 1.5-inch piping. So right away out of the gate, we're going to be converting over from 1.25 to 1.5 in single unit applications. In multiple units, we just pick the number of units and the size of the heat pump, and that will dictate then what header size we will be using. Okay. Storage tanks. We don't see this often, but there are some rules to follow with our use of storage tanks. And this is right out of the manual. This is not something I'm pulling out of thin air, but we are familiar and accustomed to doing reverse return. So the first in, last out principle. But this product wants to see no more than 10 tanks in a bank of storage tanks. That way, they're all similarly sized. We have even pressure drop, but then there are, again, no limit to the number of banks of 10 storage tanks. That would be a fairly sizable job. I don't know how often, if at all, that will come into play, but that is one of the guidelines that is worth noting in that manual. All storage tanks must be the same size so that we have that even drawdown, that even pressure drop. This is fairly interesting on the water side. We are sourcing these units. They are coming to us from the Rheem family, but it is coming to us with an 11/16 fitting that is ABS. So it's your ABS pipe. And Devin, I don't think Devin is here today. If he's online, I'll double check here. Yeah, I don't see him joining us today, but Devin spent some time trying to come up with a method to get us to transition over to 3/4 inch PVC Schedule 40 so that we can take that to your sanitary sewer. This is going to produce condensate, and we want to be able to transition over to that, the standard, typical size of 3/4 inch, or even on multiple units if we have to upsize to 1 inch. But this essentially is a 3/4 inch street elbow, meaning that if it's not a socket and you have this spigot side right here on the street fitting, that is the same as pipe size. And the inside diameter of that pipe size will glue on over this 11/16 pipe. And again, it's a bit of a non-standard US dimension, but we have found that a 3/4 inch PVC Schedule 40 pipe will actually glue right on it. I would recommend that you use a hot glue, an all-purpose glue, when transitioning from PVC to ABS, but that's very common in the US when we're transitioning to different types of material. Any questions on that? I was very proud of Devin for finding this solution.
Yeah, I just wanted to kind of circle back to that question that was asked. I think it was from Brian on the low ambient.
Okay.
I did want to kind of point out something I found or that's in the use and care that might answer that question.
Okay.
So when you're in a primary secondary configuration and you go into the low ambient mode, the low ambient booster will operate instead of the heat pumps if 50% or more of the heat pumps are in fault. So if you have a single heat pump, once it goes into that default mode, that low ambient or defrost mode, then it's going to lean entirely on the low ambient backup. And we recommend that the low ambient backup is set for 140 degrees. So the auxiliary booster or the low ambient backup will remain active until the water heater fault is cleared, or until it reaches that set point. Yeah.
That's great advice. I think I will include a reference to that. I'm still working through, how to best go to market with these presentations. And that is a very good point, David. So again, thanks for sharing that. I think what I'll do is include the reference to the page number in that use and care manual speaking to that. That's an excellent observation.
Comment here on the dissimilar materials, the dissimilar pipes.
Yep.
I would highly recommend that we not tell contractors or others how to join the pipes. And here's why. For 8 years, I worked for T. Christie Enterprises, maker of Red Hot Blue Glue, and they did all different types of solvents and cements in that. Mm-hmm. And had good working relationships with the guys at Spears and IPEX Pipe and those. And mm-hmm. all of them would get legal situations going on where the contractor had used the wrong solvent cement. For example, Christie's Red Hot Blue Glue is designed for PVC. And you would have people would say, oh, it's hot enough chemically, I'm going to use it for ABS. I'm going to use it for CPVC. I'm going to use it for polypropylene. No, it's not recommended. And the piping manufacturers will take those failed joints, cut them open, find out what glue is used, and then it goes to the attorney. And that. So what I would say is to the contractor, find a approved joining method that meets the piping manufacturer's requirements and the plumbing code.
Excellent advice. That's fantastic, Kurt. Thank you.
Yep.
Yeah. Why create an issue for ourselves? That's great experience. Thanks for sharing that. Okay, on to the air side. And, you know, the air, just like it is with our fossil fuel cousins, the air is a big driver of efficiency and performance. So we're going to spend a little bit of time on this air side. Here, let me back up here. And so this chart, it's, you know, what's the purpose of showing a chart like this? Because there's no way to digest all of this data, right? But there is a message here. There is a message. And the message has to do with your supply water temperature, let's say 110 degrees, right? That's the temperature of the water, excuse me, over here on my vertical axis, 150 degree, 140, 130. Here's my water temp axis right here. And here's my ambient air axis over here. So if I'm in a territory or a region where I have the availability of 100 degrees Fahrenheit of ambient air, and I have a supply temperature of 140, I quickly do the math and I can say, look, I'm going to get into this range of COPs. And COP is nothing more than coefficient of performance. So in practical terms, we need to start understanding what a COP is and what drives it. In that, for instance, let's take an X-Fire water heater. In full-on condensing mode, we might be 96% efficient. So that would be 0.96. The fact that we're using this heat pump water heater, it now has a value above a fractional number in 3.76. So if we put in $1 worth of, you know, $1 worth of energy into the X-Fire, we're going to get 96 cents of usable hot water out of it. Conversely, with the heat pump, we put in $1 worth of energy, we're going to get a multiple of 3.76 at that temperature, or rather here, 3.63. So we're going to get more energy out because we're extracting that ambient air temperature. So ambient air temperature and our supply water temperature, the lower we can make our water temperature and the higher the ambient air temperature available, the higher that efficiency. And this is a big driver in our engineering community to ASHRAE standards. They need to be above a certain threshold. So again, in the Sun Belt, in warm climates where we have high ambient air and moderate water temperatures, we can get into some very healthy production, right? So we said earlier that a 60,000 BTU unit, well, that's at a given ambient air temperature and water temperature. But if I can get into lower water temperatures and higher ambient air, now look at my performance. I'm doing a very good percentage more in production for harvesting those BTUs. So again, that ambient air temperature is a big factor in design for how much production you can actually see. I'll give you an example of this just in a minute. So this is on the HP DH60s. And again, just another way to look at this as a grid is water temperature on my vertical axis, ambient air on my horizontal axis, and then over on my right axis, you know, the lower my water temperature and the higher my ambient air, the better my performance, right? So this is I think a fantastic way to look at this. Again, thanks to Abby, my manager, for being a spreadsheet and Excel spreadsheet guru. She built this, and I think it tells a very good story. It's not something we have to memorize, but if you put this in front of your engineering community, they're going to say, I get it, okay? I need to be operating up here instead of down here, right? If I can, at 50 degrees ambient and these high water temperatures, I'm getting into some negligible performance, still higher in relation to what an X-Fire would do, but my BTU capacity then is somewhat tainted compared to what potentially could do in another avenue. Does that make sense?
Absolutely. Thank you.
Yeah, good. So at the factory, we've had some time in the hot lab, the hands-on lab, where we took a 60,000 BTU unit, the smaller unit. We paired it up with a 120 gallon storage tank. It was roughly 70 degrees ambient in that hot lab in Oxnard. And we used a supply water temperature out of the unit of 120 degrees. In practical terms, I would say this is practical results in that lab. We got about 60 degree rise in 60 minutes, so about a degree per hour in this scenario. Well, to me, I like these types of things for actual performance because now we can see what the unit is actually doing. We can look at the BTUs, and many of you have sat through our presentations know I use this quite regularly, fill in the blank, right? And if we have 4 values and we know 3 of them, it's easy to populate that 4th value. Well, in training, we also talk about this where I typically will say if we know 2 of these values plus this constant, we can always populate that 4th value. So here's where it becomes important. Again, don't get hung up on this verbiage of a constant. This is just a known value of the weight of a gallon of water times 60 minutes. It's very well known in our industry. For you math majors out there, this actually equals 499.8. But for simple math and for practical terms, we use 500 as a constant. Well, the value proposition is if we know 2 of these values plus the constant, we'll populate that 4th value, right? So here's where I think this becomes important. We can take the value of time off of here as it pertains to GPM and just do gallons per hour, right? So we know that we had 120 gallons that was heated in that scenario in the lab, that 120 gallon tank. Here's the weight of a gallon of water. We knew we were getting about a 1 degree rise, right, per minute, so a 60 degree rise an hour. That roughly gives us 59,000, just under 60,000 BTUs. And for me, I go back and say, let's extrapolate that and go back and say, where am I at? Interpolate, really. So with 120 degree water temperature and that 59,000 BTUs, I knew my COP, my efficiencies were somewhere in this realm, pretty healthy. You see how that works a little bit? I think it's very good to see what we're actually harvesting. What was my temperature rise? How are we actually performing? And that's with a 70 degree ambient air temperature. Think about a sunny day or a warm ambient air temperature and what those production numbers are going to do with that 120 gallon tank, or again, multiple units. And this is even the smallest unit. So let's get a pair or 3 or 4 of those 135s coupled with this. And now you're going to start to see where we can start to shine, in commercial applications, because we're banking on that stored water volume. We might have a dump load, but then have the rest of the day to harvest and recoup those BTUs. So as it pertains to applications, we really want to focus in on your specific region. What is that supply water temperature? What is your ambient air temperature? And again, maybe looking at these minimums here and what that production number would do. Does that make sense to everybody? So on the air side also, we know that that warm ambient air is fantastic. That's what we're extracting our heat, but maybe we don't want to be dumping that cold air back into the space. Maybe we want to duct it out somewhere, right? So we do have duct kits available. We're actually going through the brochure right now that is currently living online, and we're actually adding these ducting kits, as available options. There are some rules and regulations that we need to, not regulations, that's not the best choice of words. There are some guidelines if we're going to do ducting, and it has to do with our inches of water column for our air pressure. I'm actually still backfilling this. I apologize. It's still just a bit incomplete, but more in the future as this presentation goes out the door once we've officially launched and start shipping. So if you're interested in ducting that cool air, we have to meet those water column criteria. Right, that's just an example of what some of those guidelines are going to look like if we're dumping that cool air to a different space. So you can see based on, go ahead.
A quick question, that ducting, is that only for exhausting it, or can you also bring air into a room to heat the water, have the heat pump work? Or is it only exterior that those can be placed?
Yeah, that's a great question. I will follow up on that. This has been a topic of discussion because we have talked about how to get us that warmer ambient air if we've got an air recovery or air exchange going on. If we're bringing in outside air direct and conditioning it, and then we're dumping that warm air, why not feed that warm air right back into where that intake is? So there is some discussion about that possibility. I can honestly say I don't know that I have an accurate answer for you, but I will follow up with you. That is a fair question, but I don't know that I have the answer to that on the ducting side. It looks to me like on the ducting side, it has more to do with the exhaust than the intake. But I'll follow up. That's a fair question. I'm sorry, who asked that question again? I didn't quite catch that.
I'm sorry, what was that?
Okay, Randall, I just needed to see
Okay.
who was asking that question so I can follow up.
All right, perfect.
Yep. So again, if you look at air, you understand that really is driving that efficiency and the performance, and we can do some really good things. Now, again, as we said earlier, on the vapor compression cycle, the refrigerant, we are using R134, and it is a single speed compressor. A lot of people in the industry are using multi-speed compressors or variable speed compressors. The brace plate heat exchanger is a vented double wall, but this is all self-contained. This is not going to require us to interact on the installation side because it is sealed for us. So it makes this side of it fairly quick and simple. Now, down the road, when you do our level 3 for startup and commissioning, maintenance, and troubleshooting, I will show a couple of slides on the programming where we can go in and check what those pressures are, if they're adequate, if that vapor, or rather if the refrigerant is at the necessary charge levels that it should be at. So more to follow on that, but this really does take a comfort, it does add a comfort level to mechanical contractors and plumbing contractors knowing that they do not have to interact with that refrigerant process because they might not be licensed in that, right? So this is a big factor that we want to talk about.
Have we done a little pushback on the future development because the 134A is being phased out, as well as it's requiring HVAC is requiring at least 2-speed compressors?
Right, Brian, I love the way you think, Brian, because I think the same way. So now I'm going to do the cardinal sin of presenting, and I'm going to drop out of presenting mode. I do have a slide 41. I will say this for future reference. I'm going to go back here. So I've been doing some due diligence on the different refrigerants that are being used. And what Brian was talking about is if you go back in time, maybe to like Dave Baker's age, decades ago, right? Love you, David. Maybe they had Freon systems. Well, that CFC, that chlorofluorocarbons have been phased out. That's why you no longer can use Freon, right? There is an ozone depletion potential that's looked at, a global warming potential that's looked at. So now all these other refrigerants, to Brian's point, are looking at a period of time where they also will be phased out. Now, this is a work in progress. I wasn't going to include this in, but the industry is looking at other refrigerants that are not going to be phased out, that don't have the ozone depletion potential, that have very modest global warming potential. Pardon me. And I think down the road, what you will see is you will hear more about CO2, and you will also hear about propane. Even though propane is flammable, they're talking about the use of these as potential refrigerants that give us these working temperature ranges. Again, this is a bit open-ended, but since Brian asked the question, this is what's coming. Eventually, the R134 will be phased out. I don't know the time frame for that, but again, we are going to look at different types of refrigerants that are going to do multiple things for us. Number one, not be susceptible to these factors, but they will also get us down into these lower temperature ranges so that we can harvest, we can still do waste heat recovery or heat rejection in sub-zero temperatures. I mean, so this is kind of a glimpse into the future of what's going to happen. Okay, so I don't want to speak too in depth on that. I'm going to go back to that vapor compression cycle. But Brian, does that give you a glimpse into what we're going to be talking about into the future?
Yeah, for the refrigerant, yes. I just know that a lot of HVAC is switching to a requirement for at least two-stage compressors, two-speed compressors, that is.
Agreed.
So also that I didn't know if it's probably getting way down in the weeds, but also a variable flow
Right.
on the refrigerant as well. It gives you multiple options of takeoff.
Agreed. And I know you're a trainer, Brian, and you've obviously got some good experience under your belt. What I have to do as a trainer is remember my role to train. I'm not in engineering. I can be a part of those conversations, but those decisions are made and happen in a different office than I possess. So we'll let those engineers do their thing. We'll let them figure out that path, the feasibilities, and all of those things. I'm not using them as a scapegoat, but my role and my function is to get the message out as we've launched it. Down the road, another issue of this air to water heat pump with a different refrigerant, it's going to have some different characteristics. We're going to follow this same template, but I think instead of capping at 40 degrees ambient, you'll see 0 and -10 and -20 and still be able to harvest some BTUs.
Oh,
So
I appreciate it. The only reason I'm asking is I know that they're going to make this development, but we are targeting people that are plumbers that actually have multiple roles. We have plumbers and HVAC, and we're seeing a lot of transition to be able to get both in there. So the people that do the HVAC are going to be asking these questions.
That's fair. That's fair. The beauty of our industry is there are multiple correct answers, and I think we're going to see more multiple correct answers as we move forward. But you're asking the great question, and it's the one that's going to be needed to be answered in a period of time. And stay tuned, and we'll let engineering do their mojo and product management do their mojo so that they can come up with that best solution as a turnkey package.
Okay, good. I'll just tell them in progress.
Agreed, work in progress. And I love hearing those comments, Brian, because if you're in my position, where do we stop? Where do we leave it? how much information is too much information right now? I
Oh.
struggle with that sometimes.
Hey, Paul,
Yes.
just to address Brian, this is Aaron Weaver, East Coast Regional Sales Manager.
Yep.
Product management has made us aware, like Paul has made mention, that we are aware of those things that you mentioned and those changes that need to happen, and they are working towards that goal.
Mhm. Well stated. I like it, Aaron.
Works for me. Thank you.
Yeah. Aaron Weaver, fantastic trainer in his own right. Okay, on to electrical. Well, I'll have a moment of pause. Any other questions with the refrigerant side? Okay. On the electrical side, it's surprising as I was assembling all this, there were a lot of slides pertaining to electrical because this is an electric box that ambient air assist. So there's a lot going on electrically. There's basic requirements to power the unit, the relays for the circulator, the sensors, staging multiple units in cascade. So there's quite a bit to discuss here. So here's your usual suspects, your phase and your voltage, your minimum circuit amps, and how much power does the unit actually use while it's running, right? So these are some of the basics that we'll be going forward with. On the front, or rather on the back, that was really our wet side. Plus, you have 2 ports of entry where our sensor wiring enters and exits, if you will. On the front of the unit, you have these really what looks like knockouts, but they are grommets. And here's where we can bring in our power and our line voltage, if you will. We'll talk about LAN, local area network ports. We're going to be using those when we're tying multiple units together. We'll just consider that to be our cascade wiring, a term that you're probably familiar with, right? So again, more to follow, but just a glimpse into the cabinet where you're going to find your tank sensor and building sensor, as well as on the front where you're going to find your line voltage for your circulator and your primary power. So if we remove the cover and covers on the front of the unit, you will see this grid on the 60, the smaller unit, and I've expanded this so you can start to see where we're bringing in primary power. Remember, this is 240 volt single phase, 208 single phase, and this is 60 hertz. Very easy to connect to. Now, on that same unit, I go ahead and talk about the wiring of the circulator. It's a little bit hard to see here, but here's where my pump contacts are, right? And these are dry contacts. So I'm switching power through these dry contacts on out to that circulator. Okay, on the larger unit, that is 480 volt 3-phase. So similar in proximity to the 60, but on the 135, that terminals are just a little bit farther to your right, but again, very easy to access, very straightforward. The circulator is, again, up on this top left, dry contacts. Think about it as a definite purpose contactor, if you will. So at present, this is what your wiring will look like going to that circulator. Additional contacts, a lot of different ways to use these contacts or relays. If you're using a louver proving for air or maybe additional fan to exhaust, you can use these terminals. One of them is a 24 volt wet contact. It's at the FA and N terminal. And then conversely, these 2 terminals of VF, those are dry contacts that we can switch up to 5 amps through. So again, a little bit of versatility there if you need to switch power or maybe bring on external components, field supplied components. You have some options here when the unit is running. Also, those would also be used to energize a coil for potentially this single pass. I think I've got some more work to do on illustrating this. This came to me fairly recently, but in a single pass unit, I need all these units to fire. How do I engage that call for heat? This is one example. I don't know if this is in the manual. This might be in the manual. I'll have to go back and check. Slide 50 if it's in the manual. Questions?
Can I just
So
make
you
a
don't-
slight
Yeah, go ahead.
comment? When dealing with electric tankless, ideally we want to make sure that that pump is shown pumping into the supply side and not pulling on the outlet side. We want to maintain that pressure going through those tankless heaters. On the inlet side of the pump is going to drop, and we don't want to do that.
I concur. So what Randall is saying, this drawing, this circulator here on the suction side should be upstream of these heaters, and then the discharge side would be on the downstream, correct?
Yes, that
That's
is
what you're
correct.
suggesting?
Yes.
Yeah, okay. I'll confirm. That's a good observation. Circulator placement on slide 50. So this is the second time I've given this presentation. I rework presentations and continue to revise and amend. So your feedback is great. I don't presume to have all the answers, but I'm definitely going to follow up and make sure we have the correct answers moving forward so that when this goes out the door, we are adequately supplied to answer all these questions correctly. So again, I appreciate your patience on that. So then the multiple units, they use this LAN wiring, local area network wiring, and it is a proprietary cable. So I'll show that at the end of the presentation that there are specific part numbers for these cables, and it's essentially a plug with 2 points that plug and play. So very, very simple to wire. So again, just as an overview, let's say, here's what my wiring potentially would look like on the low voltage side. So this would be my leader, this would be my member or my follower, and then I would also go out to here, actually this would be my leader, and this would be my follower. But now I'm sending out my system sensor wiring and my tank sensor wiring. And here's where those tie into. You know, if you were to take that cover off the front of the unit, right below the display, you're going to see all these little terminal blocks. And they're very easy to identify. And we can stage and rotate and cascade up to 4 units. So the leader will not have anything going to it other than exiting. That LAN cable will then plug into the next unit. And then you'll put a jumper across DIA3 and DIC1, and then so on. This will feed the next unit, DI4 and DIC1, and then conversely, that last unit. Again, very easy to do. Here's the reference of the part number. And we recommend 22 gauge stranded as your jumper. Those would have to be placed. They do not come as standard. Any questions with wiring units in Cascade? It's pretty straightforward, pretty easy to navigate. Simple daisy chain wiring.
Paul, is there a minimum stranding requirement for the 22 gauge, or does it matter?
Fair question, Jared. I'll double check because I believe 22 gauge was the minimum.
Well, no, what I mean is in 22 gauge wire, you can have multiple different numbers of strands making up a 22 gauge wire. That's what I'm asking. Is there a minimum number of strands required?
Okay, minimum strand count. I will find out. Fair question, Jared. Thank you.
I noticed that the first member gets like jumped 13, right? And the other one's 14. And the 13, I'm not clear on that part, why first and second are not the same.
Sanan, I'm not sure I understand your question. Could you repeat that for me?
Sure, I'm following these. I'm following these. The leader, first member, second member, third member, right?
Okay,
I'm seeing
all
the
right.
jumper wires. Like the first one, the first member has between D13 and or DI3 and DI, and then the other ones just DI4 jumps. I'm not clear why they're different. And the third one has all jumped together. They go back to D13 and D14. I'm not clear why these jumpers are different.
Okay, well,
That's
I have a partial answer, but let's work through it because that's a fair question. The leader, when we don't have any jumpers here, let's just suggest that this knows it's the leader. And we're now identifying, we're telling each unit which one it is in the sequence when it's communicating with the leader. So to get this unit to understand that it's the first member, we're going to put this jumper. And by putting the jumper on these terminals, it now understands it's the next one in sequence after the leader. And then the second member and the third member. These are the jumper configurations from the manual that let the unit recognize where it is in the sequence of cascade.
got it. Thank you. Thanks for clarifying that.
Okay. I had to think about how to phrase that, but that's the best way I know how to describe it.
That's excellent. That clarifies it. Thank you very much.
Okay, good. Any other questions?
I got one, Paul.
Yeah, Aaron.
Hey, Paul, I got Eric Connor with me. We actually have the factory supplied cable that actually could be ordered to do that jumper sequence.
Okay, let me feedback what I heard. Are you talking about the LAN cable?
Yes.
Okay, so you're right. I have identified sequentially it's communicating unit to unit to unit, right? That is one wire in daisy chain sequencing that communicates all of these. That's absolutely true. But when we do that, Peter, we still need to have the unit have a unit identifier of where it is in the sequence. So you're absolutely right. This is a part number that is an optional cable available when you order the unit. Highly recommend them being utilized. Okay, so that's step one. Step two, and to Sanan's point, is we now also need these jumpers that are field installed to identify the unit where it is in the sequence, whether it's the second, third, or fourth unit. Does that make sense?
Yes, it does.
So it's a combination of the interconnection of the daisy chain wiring as well as the jumpers are going to give us that ability to communicate amongst all units.
That's fine. Yeah, and so you're not basically using this the control screen to set the number of the unit. You're using a jumper.
Well, Peter, another good observation. You're actually going to do both, but we're going to talk about the programming and commissioning and programming these as number of compressors, which one is which. So more to follow in the level 3 when we do startup and commissioning and programming. In fact, when we're done with this today, I'll go ahead and bring up my level 3 presentation and give you a glimpse into that. Is that fair?
100%. Thank you.
You bet. Okay. Sanan, good question. Is everyone else good on the wiring, what it's going to take?
Just one last question.
Sure.
What if loses communication, the cable? How would they react? I mean, they will just.
Good question. The way I'm understanding it is that if we have power to the first unit, right? If we have power to the first unit, but the unit goes offline and still has power, it's still going to function as the leader, and all of these are going to understand that it's still connected, even though this one is not in operation, okay? If we lose power here, then we lose that communication and our units are then offline. We are not then communicating as that there is a load or a demand. That's how it was explained to me.
All right, got it.
Good questions. Anything else? Other questions? Okay. I do have a screen coming up though, Peter, about the two different modes of cascade that we can look for. Okay, so I'll talk more about this in a minute. So now we also looked at that installation. We know that even if we have two tanks that are the same size, if they are piped properly in reverse return, we're going to get even drawdown. So presumably, and we're banking on the fact that we're going to have the same temperatures in both tanks. So the lead unit, the leader, will have one sensor to B10 and ground. I didn't illustrate the second wire here, but these are not polarity they are polarity sensitive. So B10 and ground here. And then that is for my tank sensor. B11 in ground will be my system sensor. So what is my supply water as opposed to my stored water temperature? So those are the two sensors that we will be wiring from that leader. Again, just going back to those terminals I think I'm going to remove this slide since I talk about it in the electrical, slide 54, remove, and got by me. Since we talked about this with, if we're using those ducting kits, I showed you on the electrical slide where that 24 volt wet contact was and that 5 amp dry contact was. So again, just make note, we can talk about if we're bringing on an ancillary fan to move that air to a different space. Modbus. Modbus is something we can do. In the appliance, we have a port here that if you order the optional Modbus card, this is where it's going to plug into, this J6 terminal. And we'll spend quite a bit of time in that level 3 presentation for startup and commissioning. We'll talk about Modbus and all the different aspects, programmability that we have available to us. But from an installation standpoint, if you order the optional Modbus or BMS card, this is where it's going to plug into. And then finally, service clearances. Service clearances aren't important because, well, of course you caught me, they are important. So these are the clearances that we want to see for that evaporator coil, the back of the unit, the front for the display, as well as for our water connections. Also on the horizontal units that discharge vertically, right? So the air intake comes in on the horizontal and they discharge vertically. We need to have room on top of that so that if we were ever to have to access that fan, right? So they say in the manual to leave enough room for an agent to stand on it. I'm not sure how to extrapolate that from a service side, so maybe some of my colleagues have some understanding, but I guess the height of the agent is how much room you need to leave there to be able to access and get above that unit. Again, just the chart right out of the manuals. Generally, I don't like to cut and paste directly in and out of the manuals. I like to have a little bit more visual interest there, but here's the important for your standard dimensions. I think it's important to include these since this is typically noting where we're placing the units. And there's the 135. So the previous slide was for the 60s, and here is for the 135s. Now, a couple of things as I was looking through the manual, I thought it important to include that unit is built with some pitch to it. And so that if it does go into a defrost, it will drain properly, right? So don't try and level the unit, just put it on a base that is level don't try to individually level that unit, if that makes sense. Do not tilt the heat pump more than 45 degrees from vertical. I think this is true when you're moving a refrigerator. You don't want that refrigerant, to get a particular way. So if you do, it needs to sit for a period of time to settle. So this is in keeping with what you might have already seen with other refrigerant-based equipment. And this is in page 14 of the installation, or rather the use and care manual. They don't call it an installation and operation manual. They call it a UC manual, use and care manual. So just a couple things to note about service clearances, placement, and where initially setting the unit. I think these are worth noting. It's fairly important. Options and accessories. We are in the process of amending this. This is in our brochure at present as options, but we're also going to backfill and add losing my verbiage here, the kits necessary for ducting, as well as, what are we also adding? We are adding one other item, and it escapes me. Slide deck. Oh, stack kits, excuse me. So we have the ability to use stack kits on the horizontal exhaust units. So if they exhaust out the horizontal, out the side, we can stack those units vertically. So a stack kit will be available for horizontal units, and we're also going to add the ducting kit numbers to these options and accessories noted on your brochure. I had to go to my notes there for a second. Okay, so I'm going to pause and ask any questions, any slide numbers we want to revisit. I do have some slides written down from David Kelly, from Kurt, from Randall, and from Jared. Any other questions, comments out there? I will be following up with you guys. We will be sending this presentation to our recorded webinars that lives on raypactraining.com. But again, comments, questions?
Is there any thought in the future of having solar as a assistance for the fan motors and compressors, like they do in HVAC?
Solar?
Yeah.
Like solar thermal or solar PV, photovoltaic?
Be the PV, solar PV, so it can assist the fans and the compressors like they do in the HVAC.
Yeah, that's a fair question. Solar PV photovoltaic is a DC, and then they can, convert that power back to AC with microinverters and so on. I don't like giving cheap answers, but the cheap answer would be, if you're running solar photovoltaic, how you harvest that and store and use that power, as long as it's done by manufacturer's instructions, as long as we're receiving the proper voltage, I don't see any limitations to seeing photovoltaic supply the necessary power, but it must be in AC, not in DC.
Right, but I was just wondering if we were going to make the heat pumps where they have their own solar panel that would be tied into their compressor and their motor to help assist to cut down the efficiencies.
I have honestly not heard of any such discussion. That's again at the engineering level and design. So I don't know if I would even be made aware if they were working on something like that. But I don't see that happening anytime soon. Just from a practical standpoint, we're going to focus on production of domestic water. Give us the power and ambient air. Here's what we're going to be able to produce in terms of gallon per hour and temperature rise in BTUs. So I think your question is sage and it's fair, but long story short, I don't believe we'll see that as something we pursue.
All right, fair enough.
Okay. All right, I'm going to give you a glimpse into the L3 presentation real quick, because I want to talk about the cascade wiring real quick. Start commissioning. Again, we're going to do this L3 presentation. But as it pertains to Cascade programming, Cascade. Okay. So one of the features in Cascade will be when we go in and navigate, and I'll give you all the how-to. I'll give you all of the necessary handouts to help you navigate, right, on this control sensor. So if you have multiple units, you have the leader, you have the second unit, the third unit, the fourth unit. You literally go into here and you tell the leader how many compressors are being staged, right? So again, we're going to navigate to that screen. We're going to tell it how many compressors are going to be in that sequence. And then the default is simultaneous. So in other words, what happens when I go to simultaneous, it's going to look like this. Staging will be simultaneous or staggered. And here's what this is going to look like. Oops. I thought I was getting you to it anyway. Maybe I misspoke. I'll go to this one because in the I'm going to give you the top 10 programmable. There's a myriad of parameters to access and program, but I will say if you know a top 10, top 15, you'll be fine. But here, you'll go in and learn to navigate to this very quickly, and then the number of compressors will be how many units are being cascaded. And then the compressor staging will be simultaneous or staggered. And staggered will look like this. And I'll have a better example in a diagram. Let's say we have 4 units in Cascade and we have a single storage tank. The staggered selection there will say that if I have a 10-degree differential, right? If I fall that 10 degrees from 140 stored water temperature, I fall to 130, bring on all 4 units. And all 4 units are going to stage and stagger equally at about 2.5 degrees. 2.5 degrees times 4 units will give me that 10-degree differential. So as we supply heat to that storage tank and I creep up within 7.5 degrees, then the 4th unit will fall off. If I creep up to within 5 degrees at that point, the 2nd unit will fall off, and so on. So the default is simultaneous, but we can also do staggered to give us an equal rotation of set point. And these will stage and rotate for equalizing runtime. So just a glimpse into what that staging multiple units will look like if we do it correctly with that LAN cable and those individual jumpers noting and giving self-identification to which units are in what sequence. Does that make sense? And again, here's an example of what it's going to look like when we do the L3. Here's how we're going to push those buttons and learn to navigate through. If you were to come to the hot lab, I will have this laminated and attached to the unit. We're going to get very, very comfortable navigating this menu. It's not going to be difficult as a learning curve. So again, I look forward to doing that level 3 presentation with you, startup, commissioning, programming, troubleshooting. I think you will like it. Okay. Now back onto the final slide. Again, I'm open to questions. There's my email if you want to do some follow-up after the presentation. I'd be glad. I will follow up on those questions that were asked to David, to Kurt, Randall, and Jared. So appreciate all the healthy dialogue. If you would, if you would take out your phone and just put it in camera mode and scan that QR code, it's going to ask you that series of questions. How did we do today? Was he knowledgeable? What can we do better? What else would you like to see? We're open to your input. I know that The second time now that we've given this presentation, we'll continue to groom it, we'll polish it, we'll make it better, we'll take your feedback, we'll add necessary slides in. So again, I'm not at all intimidated by your comments or questions. I welcome them. I would love to hear more from you so that we can continue to make this a really good mousetrap and make it really easy to get out, installed, and used in the systems. Okay, comments, questions? Fire away. Okay, doesn't appear to be any questions at this time. And we are actually over by about half an hour. So this went a little bit long. Well, thank you, everybody. Thanks for joining us. And I look forward to future dialogue. And I'm sure we're going to do this presentation again, polish it, and continue down the road of making this extremely usable. So thank you, everybody. Take care. Have a great day.
Thank you, Paul.
You bet. Thank you, Ray.
Thank you, Paul.
Thank you.